All right. So 9 people. Can you listen? Hear me? Hello.
Yes, yes.
Yeah,
Yes,
yes.
sir.
Okay, yeah. Someone is asking for the average marks. Okay, so yeah, let's see. Today evening I will email you. Okay. What is the average only? So I need to look at the marks also. So I asked what about the marks to Professor Sangdeep. Once he send me, then I will send you. All right. Okay. Any questions from the last class? Where are the other people? Any class is going on? So I hope you enjoyed the quiz day before yesterday, right? The questions are very easy.
Yes.
All right, let's start. Okay, so 11:05. I normally wait 3-4 minutes. So surprising. What happened? Everyone went home for Diwali or something. Okay, so let's start. If you have any questions, you can tell. Can you see my slide?
Yes, sir.
All right. So last time we discussed about the linear free energy relationships, okay, on changing the substitutions of an aromatic ring, and that is the Hammett plot or Hammett's hypothesis. So the part one we discussed that references benzoic acid. So how the acidity will change on changing the substitutions on the aromatic ring of a benzoic acid, or how it will change the acidity of the benzoic acid on varying the X, that is the substituents or different functional groups. So that will detect what is the value of sigma, right? It's a sigma. So sigma is log KAX divided by log KA. Ka means simple benzoic acid and X means substituted benzoic acid, right? So this is the table. Okay, so this is already, because you know that, okay, so for changing the substituents here, okay, suppose chlorine, bromine, methoxy, methyl, ethyl, propyl, isopropyl, whatever the functional groups or substituents you can get, you can easily derive what is the value of Ka by, you can easily get the value of Ka by experiments. Okay, so the sigma is constant for a particular functional groups. Okay, and the values of sigma has already been calculated. Okay, already been calculated experimentally, and this is the values. So you can see this is a table I just copied from a book. Okay, so when NH2 is there, so definitely acidity will increase or decrease. Acidity will decrease, right? That's why you can see that it is negative value. Now this is the position sigma value in meta where the NH2 groups are there in the benzoic acid. Para positions, okay. Plus minus I'm not going to discuss about this, forget about this part. Okay, I just copied, so disregard this part. So let's talk about the sigma and para. Okay, so you can see here NH2. Okay, so when it is the para positions or meta positions, okay, so what will happen? It is basically electron donating group, so it is decreases the acidity. Okay, so sigma is negative. So if you look at all the electron donating groups, okay, suppose these are the electron donating groups. Okay, methyl, methoxy, okay, t-butyl. So you can see here, so many when they are para positions, because they are either conjugated, okay, like methoxy, or they have plus R effect because of the high by conjugations, all values of para positions are negative. But couple of cases, suppose methoxy, when it is meta positions, it will act as a electron withdrawing group. Okay, that's why you can see the sigma meta is positive even though sigma para is negative. Does it make sense? This is experimental value. Does it make sense? So you can see here methoxy 1 is quite interesting, definitely as expected that para it is a sigma donating, but when it is meta, this is acting as a electron withdrawing groups. Okay, so this is positive value. Okay, so if you go down, you can see that when the functional groups are electron withdrawings here, okay, you can see the bromine, iodine, bromine, chlorine atoms are there. Okay, so if you can expect that iodine to bromine, their electronegativity is decreasing, so sigma para value will always increase in the positive range, right? That is expected. So if you increase the electron withdrawing power of the groups like cyano, nitro, you can see you will get the sigma para value very large. Sigma para or meta doesn't matter. Okay, because regardless where this is, it will always be acting as a electron withdrawing groups. Okay. So you can see that for cyano, nitro, the sigma para value is 0.70, 0.81. Okay, so this is the plus. Plus means, so if you have the substituted nitrobenzene, 4 nitrobenzoic acid or 4 cyanobenzoic acid in the para positions, the acidity will be much larger compared to simple benzoic acid, unsubstituted benzoic acid, because cyano or nitro, they are very strong electron withdrawing groups. So acidity will enhance as expected, you know, from your high school knowledge, right?
Yes, sir.
So are we only looking at I effects or are we also looking at M effect? Like
Any effect, I
inductive
effect,
effects
R
are
effect, okay, R
so
effect,
combined.
resonance effect,
This
any
these data
effect.
would be combined, right? These data would
Yeah,
combine
combined,
this.
combined, combined effect. Because when it is a molecule, you cannot distinguish, right? Okay, I am putting these substitutions. This I will detect that. Okay, chlorine, don't go plus R. Okay, only go and detect the I effect. You have no control, right? So what are the effect possible? This is the combined effect. You can study separately, but atom will dictate whatever it wants, right?
Sir,
Yeah.
in the case of NH2, when it is at meta position, it does not act as a plus R group. Oh, basically, it has no conjugation, right? So it
Yeah,
only.
but it's experimental value.
Yes,
But you
that's
can
what I
see
was
it's
bit negative.
true. It's true, but it has, what is the value? It indicates that in the meta position still it has some kind of basic electron donating power is there. Okay, but what about the value? It is very small. Have you seen the value?
Yes, sir, very close to zero.
It is close to zero. Okay, but you can see the para positions. They have the plus R effect.
Yes.
Right, the resonance effect is minus 0.6, 0.6. Okay, sigma is a log. Okay, it's not like that. Okay, 0.6 times more acidic. It's a log value,
Yes, sir.
right? It's a
Yes,
log
sir.
value. So 10 to the power. It's a lot, huge value. Okay, yeah. Anything else? But this is the experimental value. Okay,
Yes.
you cannot complain. So you need to find the solution that why. Okay, you cannot complain that this is wrong. This is the experimental value. So this is correct. Okay, so if you see some discrepancy, it may happen. So you need to find the reason. Okay, why, that is the theory comes. Hey, why? Oh, maybe this one, maybe electronic, maybe steric, something like this. We ask always the questions why. Okay, so you need to find the scientific reasons, but experiment is experiment. Okay, you cannot change the value. Okay. Okay,
Yeah.
so let's go. So this slide I also showed you last time. Okay, that Hemo, what is the second part? Part 2, Hammett is generalizing this relationship that log Ka into Ka equal to rho into sigma. So rho is the sensitivity constant. So now rho value will tell you what how much I'm coming next. Okay, what will be the charge distributions in the rate determining step, or how it changes the acidity for any kind of reactions, not like a benzoic acid or substitute benzoic acid. Suppose here you can see here, this is a, it is not a direct benzoic acid, right? You have, I circled here, this is there is a CH2 groups are there. Okay, even carboxylic acid is not there, suppose. So any kind of other reaction, suppose any kind of SN1 or SN2 type of reactions. Okay, how the charge you will create or distribute, okay, that rho value will tell you. I am coming next. Okay, so this is the rho value will tell is applicable for any kind of reaction. So it is generalizing the reactions. Okay, So first, we will discuss about what is the implications of rho. Okay, so you can see that I told you, right? So this is the Hammett equation. So if you get a plot of log k ax versus kh for this kind of equation, suppose this is an example. This is not an benzoic acid. You have a methyl groups in between this, right? This is like a benzylic benzoic acid, right? Benzylic positions, carboxylic acid is there. So whatever the kx and kh will be there, if you just plot with sigma, you know the values. So when it is H, so it is 0. So if it is electron withdrawing other than H, then it will be positive. It is electron donating, then it will be negative, right? And whatever the values it is already calculated in the last slide I showed you, right? Whatever the values it is. So we basically get a plot, and from the slope you will get what is the value of rho. So the value of rho gives you a huge hint, okay, that how charge is creating in the aromatic ring of any kind of reaction. So that I am coming next. Okay, so what is the rho? So the slope can be positive. This is a positive slope, right? It can be negative, something like this. Sorry, it can be like this. So rho will be the negative. Also the values of the slope, it can be less than 1, maybe 0.8, it can be greater than 1, it can be plus, it can be minus. So we will discuss next, okay, that how rho will help you to understand the mechanism. Is it clear? Any questions? Hello?
Sir,
Yeah.
in the part 2 of this, so the reference acid would also be here we are not taking the exact benzoic acid, right? So the reference acid will also be
Substituted benzoic acid.
Yes.
Right. So you can see this scale here. This is benzoic acid is only here. Suppose this is chlorobenzoic, 4-chlorobenzoic acid. Oh, this is my. Let me remove all. Okay. Yeah. Okay. So you can see the references. This is only benzoic acid. Suppose this is cyanobenzoic acid. Okay. This is methoxybenzoic acid. Do you understand?
Yes, sir.
4-methoxybenzoic acid. Okay. So this x-axis is the sigma, means reference is substituted benzoic acid. So the same substituents, you can see here, this is the same substituents, how it is affecting the other reactions. That is your data. Okay.
Okay, sir. Yes, sir.
Is it clear? Not same substituents, right? So if it is more acidic or less acidic, or what is not only acidic, you just basically need to calculate the rate constant. It may be the equilibrium constant or rate constant. It may not be the equilibrium. Okay, any reaction, but make sure X is same. Okay, any reactions, what will be the rate constant? Here we are discussing about the acidity equilibrium constant. Okay, but it doesn't matter, any rate constant, K value, you just need to calculate on changing the substitutions and how it is affecting with respect to the same substituted benzoic acid using the same substituents. Okay, and get the average so that you will get the plot. Then from the slope you will get the value of rho. Make sense?
Yes, sir.
All right. So this is very important. So as I told you, depending on any kind of reactions, depending on the K value, okay, this is the basically the rho. You can see this is the value log Kx versus Kh. So we are considering the log K. This is just like more general value. With sigma, what will be the value of rho? So rho is slope. Rho is slope. Okay. So you can see the rho. If rho can be positive, rho can be negative. Okay. Sigma. This is the negative. This is the positive. You look at this. Okay, you look at this. I'm coming within few seconds. So you look at this. How is this plot? Make sense or not? Have you looked at? So you can see here, suppose this is 0, X is Cl, C88 is Cn NO2, okay, and this is the negative value. Alright, negative, positive. So the slope can be positive, slope can be negative. Okay, is it clear so far? Hello?
Yes.
Yes.
Yeah. Okay, look, if rho is positive, what does it mean? What does it mean? Means, suppose this is a substituted benzoic acid, or there is a CH2 groups are there. Suppose this kind of equations. Okay, this is a positive slope for this equation, right? This is a positive. What does it mean? What is implying? Implying means from in x-axis you are going left hand side to right hand side, right? So you are increasing the electron withdrawing power of X. Am I correct?
Yes, sir.
Is it clear, right? So from left hand side to right hand side of the sigma, we are increasing the electron withdrawing power of X. Electron withdrawing power. All right. If it is electron withdrawing, then what will happen? This ring will be more negatively charged or positively charged? Can you tell me? It is pulling the electron.
More positively charged.
You have the negative charge here.
Okay.
Okay. So the ring will be electron rich or electron poor. It will pull the electron. Suppose electron charge is here. So what will happen?
So that electron will be conjugated with the ring. It will come inside the ring.
So the ring will be more electron rich or electron deficient?
Electron rich.
Electron rich because it's pulling. It's very simple.
Yes, sir.
Right? It doesn't matter it is conjugated or not. It is pulling. So this is pulling the electron. So all those negative charge, whatever it is, it will have a tendency to flow to the ring. Am I correct?
Yes, sir.
It is pulling. That's why it is increasing the acidity. It is stabilizing the anion. So if it is electron withdrawing, okay, Ka value is increasing, right? That's why you are getting the sigma positive. Why? Because whatever suppose this is not conjugated, but still you have the plus R effect. So it is basically partly negative charge is actually pulling towards the aromatic ring. It is pulling towards itself. So the aromatic ring will be more electron rich. If it is very electron rich, if it is a conjugated, even if it is not conjugated, still it will be little bit of more electron rich, right? It makes sense. That's why it is stabilizing the anion, right? So the rho
But sir,
value.
can't we say that so can't we say that since X is electron withdrawing, so it is withdrawing electrons from the ring also. The ring might be pulling electrons from.
Electron. No, wait. I understand. Okay. Electron. Okay. If it is electron withdrawing, but electron is going where? Cl minus. No. Suppose you have the Cl. Okay.
Yes,
so where the electron? It is pulling. Okay. But effectively, it is pulling from this side.
yes, sir.
Okay. So you may tell that the electron is flowing towards ring.
That we can say.
That you can say, right?
Yes, sir.
That you can say or not?
Yes, sir.
So electron will flow towards
Towards the
ring.
ring.
Okay, that is more general. Okay.
Yes.
So you can see here also I am telling here, if it is rho is positive, electron flows towards the aromatic ring in the rate determining step. If it is single step, then doesn't matter. If it is a multiple step, then rho value will tell the electron flow is there towards the aromatic ring. Indirectly, aromatic ring will be electron rich compared to the ground state. Does it make sense?
Yes, sir.
All right. So now it is clear, right?
Yes,
So
sir.
in the if it is negative value, you will get the opposite trend of the benzoic acid, because here this is the benzoic acid trend. So it is the opposite trend. So that means if you left hand to right hand side on the x-axis or sigma value are changing the electron withdrawing substituents, electron is flowing away from the aromatic rings. Okay. So you can see that when it is positive, that indicates that you have a negative charge close to the aromatic ring. Suppose like this. Does it make sense? Like this example. Here aromatic negative charge is creating close to the aromatic ring. Either it is a conjugated or non-conjugated, right? So that if you have electron withdrawing groups, there will be a flow of electron to the aromatic ring where the substituents is there. But if it is a positively charged, then what will be the K value? K value will be reverse, right? Reverse than benzoic acid. Am I correct? So on those cases, if it is the negative sigma value, rho value, then the K value will be more for electron donating groups, and the rate constant will be slower for electron withdrawing groups. That means the positive charge is creating close to the ring, opposite way. Okay, that means that electron is flowing away from the aromatic ring in the rate determining step. Does it make sense or not? Just opposite. Just opposite. Okay.
Yes.
All right. So I'm coming again. Okay, we'll give the examples. Okay, so first tell me, let me tell you what is the significance of rho and its value and its sign. Okay. So you will see that I will give you a scale. If rho is positive,
Sir, you are not audible at all.
Hello, can you hear me? Hello.
Yes, sir.
Yes, sir. Now
Okay,
we can.
let me tell you, there is some problem in the internet. Okay, in last 3 days. So I talked to CSC, and yeah, they told there is some problem going on. Maybe I mean they are checking now. Okay, I told that I have class, but last 2 days was weekend. So yeah, I going to fix. But now it is clear, right? Hello. Yeah. Hello.
Yes, sir. Yes, sir.
Yeah, yeah. Okay, please respond. Okay. Yeah. Let me finish more. Is it clear? You have any questions? No, right? Okay. So this is the
Actually,
yeah.
sir, previous slide too.
Which one?
The previous slide.
Yeah, this is the slide.
Yes.
This one?
Your voice started lagging from the
Yeah.
slide.
Oh, okay. Did you hear what I told here? No.
Yes, sir. This slide is okay. This linear free energy relationships.
Okay, so this is fine, right? Hello?
No, this slide we couldn't hear.
Oh, you
The
couldn't get it.
Yes.
Oh my God. Okay, let me know. Okay, I don't know. I some problem. I'm now actually using hotspot. Anyway. So this is now clear. So you can see here, I'm telling that the rho value is greater than 0. The greater than 0 means this is positive, right? Less than 0 means this is negative. Correct? Hello?
Yes, sir.
Yeah, okay, someone should tell. If rho value is 1, that is only because of the benzoic acid. When it is simple benzoic acid, I told you that rho value is 1 because this is the sigma. Okay. So if rho is positive, that means that equilibrium has the same pattern as benzoic acid. Okay. Electron withdrawing groups will increase the Ka similar to the benzoic acid. Same pattern. Okay. Electron donating groups will decrease the Ka. So no doubt. Now the rho value can be greater than 1 or it can be a fraction. Let's suppose 0.8, 0.7, but still it is positive. If it is greater than 1, that means it is more sensitive to the substituents than benzoic acid. If it is fraction like an 0.8, 0.7, less than 1 but greater than 0, still positive, that means it is less sensitive to our substitutions than benzoic acid. Alright?
Yes, sir.
If it is negative, that is the just opposite case. I told you that if slope is negative, that means that the effect of X is just reverse of the benzoic acid. Means electron withdrawing groups will decrease Ka and electron donating groups will increase Ka. Okay. So whenever we will use the example, then you will see that how powerful this the rho value is to understand what is the nature of the transition state in the redetermining step. Okay. Okay. So this is a rho value This is a row value. This is a row value scale. Okay. So the row value will first of all, this is the positive case, positive this side, and this is the negative. Okay. The scale is start from 0. Okay. And then 1 is benzoic acid, then +2, +3, +4, okay, +5, +6. Same case in the left hand side, -2, -3, -4, -5, -6. So the sign I told you in the previous slide that what the sign indicates. Now I am going to tell you what the value indicates. Okay, if row value is suppose +0 to +1, okay, or maybe -1 to +1. So plus minus means same effect or opposite effect with respect to benzoic acid. Now it is clear. If it is the value is 1, 0 to 1, in between 0 to +1 or -1. So that indicates that the charge is creating. It doesn't matter it is a plus charge or minus charge. Okay, it all depends. It is the charge is creating, okay, quite far from the aromatic ring. Okay. If the row value is little higher, like +2 to +4, okay, it indicates that there is a electron flow into the transition state. Okay, so there is a negative charge creating, or negative charge is creating close to the ring. Suppose in benzylic positions. Okay, suppose in the benzylic positions, it may be conjugated or may not be conjugated. Okay. It depends on all the values. If it is even more values like +4 or +5 or +6, plus means the negative charge is creating. I told you, right? If the value is very high, like 5 to 6, that indicates that a negative charge is on the ring, or maybe a negative charge is conjugated with the ring. Does it make sense? Can you hear me?
Yes, sir.
I will next slide I will come up with example. It will be more clear. Okay. The opposite way. If it is negative -5 or -6 row value, that indicates a positive charge is on the ring, or maybe it is conjugated. Okay. Positive charge in the benzylic positions or on the ring, because it is highly affected that whatever the slope, it is very high, 5 or 6, but it is negative. Negative means the electron donating group will facilitate or stabilize the positive charge. So that positive charge is creating. Okay. Number 1, and electron withdrawing groups will destabilize. That's it is negative. Just opposite trend with benzoic acid. Okay. Any questions? If it is not, then I will go for an example first. Then I think it will be more clear. Look, this is a substituted styrene. Okay, you have an alkene groups are here. If you do bromination, then you will get dibromide compound. X is the substituents, suppose is the para positions of the aromatic ring. Okay, it is similar reactions whenever you will treat with phenyl PHSCl. Okay, this will also undergo addition reactions with the alkene to give Cl and SPH. So this is a similar, isn't it? Okay, I don't know why whenever I draw by mouse, it always happens something like a scratch in the left hand side. Okay. So this is an addition reactions. Br2 is adding with alkene, and here Cl and SPH is adding. I'm not talking about what is the isotope effect, in isopeptide is there, what is the rate law. I am now directly going to about the Hammett equations. Okay, and what is the row value? Look at the row value. Row value is -5.6 for bromination, and it is -2.6 for the addition of PHSCl. So first of all, let me tell you what the rho value tells. Rho value, first look at what is the sign, negative or positive. This is negative. So negative value of rho value is indicates it has the opposite trend compared to benzoic acid. Okay. So close to the ring, there must be a positive charge is creating or negative charge is creating.
Positive charge.
Positive charge. Okay, positive charge is creating. Okay, so that the rate is more when electron donating groups are there, less rate constant it becomes lower when electron withdrawing groups is there. So the negative values is telling, so there is a electron getting away from the ring, means positive charge is creating in the rate determining step close to the ring, not on the ring. Okay, okay, maybe on the ring. So first is the negative value. Now let's do the value. The first one, left hand side value is 2.7. I gave you the scale on the top. What does it mean? What is telling? What is telling? The 2.7 is telling that the positive charge is creating, but it is quite far. Positive charge is creating somehow higher in the during the reactions in the rate determining step, but the positive charge is quite far from the aromatic ring. Okay, it is telling that electron flowing out of the benzene ring, but it is quite far. Okay, the value is minus 2.7, so it is quite far from the ring. But here minus 5.7. What does it mean? That means the positive charge for bromination either creating on the ring or maybe close to the ring which is conjugated. It is close to the minus 6. Okay. So there will be the positive charge is creating either on the ring directly or on the benzylic positions that is conjugated. So what is the possible mechanism? Possible mechanism is given here. So bromination reactions, it is actually, you can see the he is here. So the one possible mechanism is, there are two kind of possible mechanism is there. One is that brominations, I already gave the answer here. The rate determining step, a positive charge is creating on the benzylic positions so that this is conjugated. Okay, so there will be a huge effect of X. That's why rho value is close to 6. Positive charge is creating, that's why it is negative value. Okay, and what is the rate determining step? The creations of the positive charge is a rate determining step. This is the mechanism. Another one possible mechanism for bromination is also the same thing for the second case, PHSCl, when there will be a carbocation will form, a cyclic carbocation will form like here. Okay, like this you can see here. So this is also possible, but you can see here the positive charge is not conjugated. Is it conjugated? No. Is it not conjugated? There is a del plus here, so it is creating a positive charge close to the ring, but it is not conjugated. So the effect of the plus charge, that's why the rho value is much lower, 2.7. But this is negative. Is partly created close to the aromatic in the rate determining step. So the rho value will easily distinguish what is the possible mechanism, number 2 pathway or number 1 pathway. Does it make sense? Any questions? Let me know. Look at first again.
Sir?
Yeah.
So there are some mechanisms which suggest that bromination also occurs through cyclic bromonium formation. So how do we account for that?
Yes, but that is a different case. That is not for this case. Do you understand? That is a different substrate. Yeah, brominations can occur. Bromination can occur in a cyclic transition state. Okay, but the substrate is different, not for in case of styrene. All right, and if you get it, then you will never see a rho value minus 5 or minus 6. Never. you will get probably like -2 or -2.5, something like this. The second case.
Okay, sir.
You understand?
Yes, sir.
So you can account for that. So okay, now questions. Okay, I told you, right? First is the experiment. Now what is your name?
Sir, Abhijit.
Abhijit. Okay, so Abhijit is pointing a good question. There are some cases I think you may award from your high school, right? That you some cases you may find that the for Bromination reactions, the similar kind of whatever I circled here, similar kind of transition state is also possible. That's why I'm telling here. Two type of mechanism is possible. Number one or number two. How do you distinguish? So now you tell me for which cases of brominations it is likely. Okay, I can tell you, you can see if it is a bromination, then positive charge is created on the benzylic ring. Okay, that is highly stabilized by the phenyl ring. So if you just remove the benzene ring with alkyl groups, then most likely you will get the second transition state, second mechanism. Okay.
Oh, so in that the rho value will be less, right?
Exactly.
Like minus 2 point.
Yeah,
something.
yeah.
Yes.
Okay, but let me tell you, I told you from the beginning of the class from the Hammett equation. Hammett is a very powerful tool to understand the rate determining step or mechanism of an organic compound, but it is also a limited special case. Okay, it is still people many research papers people do that. Okay, but you do that whenever you will study a mechanism using a Hammett plot, you need to make sure you have a aromatic ring where you will do the substituents. Okay, so if it is the alkyl groups, then how you will determine the rho value? You cannot. That makes sense.
Yes, sir.
So the substrate or starting material must have a aromatic ring with various substituents. So at least one aromatic ring must be there. If it's alkyl, you cannot do that. So you have to rely on other methods. Whatever I told you, right? First is the red law. First is the red law. All right. So okay, look at here. So this case, there are two mechanism is possible, 1 and 2. What about the red law? Red law can distinguish this path 1 and path 2? Yes or no? Can red law distinguish?
No, sir.
No. Right? Obviously, you have to determine the red law to get the red constant, right? To get the rho value. But red law cannot distinguish these two. This is the drawback of red law, not drawback. Okay, a red law cannot distinguish. Okay, the question will come here also. Now, if you also determine the red law, then you are wrong. Okay, so red law cannot distinguish because both cases red law will be first order on respective for both. Okay, next is activation parameters. Can activation parameter distinguish between these two pathway?
No, sir.
What will be the activation parameter values, plus or negative? Entropy of activation.
So negative.
Negative, but both will be negative.
Both negative.
Yes.
Right, both will be negative. Now this problem is coming, right? You are getting more problem. What happened? Red law cannot distinguish. Activation parameter cannot distinguish. Okay, what is coming next?
Isotopic effect.
Isotopic effect. Okay, suppose you are getting a H or D here. Can it distinguish? Isotopic effect. There is no primary kinetic isotopic effect, right? The CH or CD bond is not being broken, right? So what about this case? Isotopic effect can distinguish or not?
No, sir, because in both cases it's not the CH bond is not breaking. Yeah.
Okay, but what about secondary?
So then also we won't be able to distinguish.
Yeah, it's true. It will be very difficult to distinguish because it is sp2 hybridized. This is also sp2 hybridized, right?
Yes, sir.
Yeah. Okay. Maybe some fluctuations will be there. Okay. But okay, because you can see here also if it is CH or CD, actually you may get here. You may get inverse kinetic isotopic effect. Am I true?
Yes, sir. From
SP2 and SP3. It is SP3 here. Right. You make it loose to tight. So you make it inverse here. Am I correct? Maybe.
yes, sir.
Yeah. You make it. Yeah. Maybe isolated effect you can distinguish. Okay. But you may get, okay, it is one possibility, but you can easily distinguish the last option. Okay, here is why I am giving the example, this example in the beginning. There are a lot of example I am coming next. Okay, but why I am telling in the beginning, first example is this one, because here red law cannot tell you, help you. Entropy of activation cannot help you, right? So only major thing is that rho value. Rho value can distinguish this 1 and 2 pathway. Does it make sense? Interesting?
Yes, sir.
Yeah, rho can tell you. Okay. So first, second, third, fourth. Third may tell you, but fourth one, that is the Hammett plot, can easily tell you which pathway is correct. All right. Okay, I'll upload the slide today. This is the last slide before I close. Okay. Look at here. These equations. I told you, right? Every class I will discuss about SN1 and SN2 type of reactions. I told you, right? So this is now, let's distinguish. This is the reactions of SN2, right? Am I correct?
Yes, sir.
Okay. All right. And now wait. Yeah. And this is SN1. All right, I told you, right? So look at here. This is the phenoxy and CI bond is leaving, and this is the proposed transition step, retracting step. Okay. Opposite one is the same thing, but this is a T-butyl. This is the SN1 type of reactions. See the difference. The rho value is negative -1. What does it mean? Negative means positive charge is creating in the aromatic ring slightly. So what about the positive charge is creating? So basically electron is flowing away from the ring. Am I correct? But you can see here for SN2 type of reaction, SN1 type of reaction, rho value is about -4.5. That means there must be a positive charge. Minus means positive charge is creating close to the aromatic ring. So this rho value also can easily distinguish between this SN1 and SN2. In SN2, there will be the positive charge creating on the benzylic position. Okay, so it cannot be very low. That is also supported by the rho value, that is a -4.5. Okay, but why this rho value is -1? You can see this, the O negative value change is actually dispersed in between the O minus and I minus. Okay, so you can see there is one negative charge here, right here, but here negative charge dispersed to two atoms. So here a del plus charge is creating. Am I correct? Compared to ground state. Okay, that's why rho value is negative, not positive. Okay, -1. Very light positive charge is creating compared to the ground state. Is it clear or not?
Yes, sir.
Is it clear? So in the ground state, one negative charge is here. In the excited state, negative charge is dispersed to two atoms. So effectively in the benzylic positions, there is some del plus. Okay, everything. How, what is the experiment? Effect, however, is it is effect entropy activation. It is all telling that what is changes in between the state in the determining state, ground state. How much is negative charge? is in between the ground and excited state, and will be the rho value. Will how much? Small amount or large amount, and it is positive or negative. And where it is creating? Close to the aromatic, away or far away from aromatic. All right. I'll stop here, and I'll upload the slides today evening. Any questions? Yeah. People, what happened?
Sir,
Diwali is coming,
your
that's why.
voice is so your voice is actually cracking a lot. So uh, maybe in the next class you could repeat a little bit of the last 2-3 sentences you said.
Oh, last 2-3 sentences.
Yes, sir,
Okay.
because your voice kept cracking, so it was not clear.
Okay, I'm sorry for that. This is
Yes,
the
sir.
problem of online class. Okay,
Right.
but today is a problem. But I'm sure next time it will be fine. Okay, don't
Right,
worry.
sir. Right, sir.
So, okay, so last rule I will discuss again, then I will proceed for the next. Okay.
Yes,
Yeah.
sir. Thank you, sir.
Okay. 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 Anything else? If it's not, I'll close here. Stop recording.